Hello everybody, in this video we are going to continue our conversation about quadratic transformations. So in some of the previous videos we talked about what vertex form looks like because that's what we're using for our transformations. We talked about what a parent function is, and so we're constantly comparing anything that's happening, a new graph, and we're constantly comparing it to the parent function so we can understand and identify the transformations that are taking place. So I do want to remind you that in order for this video to make a little bit more sense, you already have to have the graphs on your coordinate planes. If you do not have the graphs for vertical stretches and compressions, then I encourage you to pause the video and add both the parent function to the graphs, but also the new function so we can have a conversation focusing on what a vertical stretch and a vertical compression is and where to find it in the equation and what it looks like on the graph. So if you don't have these, go ahead and pause and then jump right back in. All right, so once you have your graphs, we're going to write in right here. This is our vertical form quadratic equation. And I want to mention that the vertical stretches and compressions has to do with the A. Now, when we talked about reflections across the x-axis, we said that the sign associated with the A is going to affect whether we have a reflection or not. It's going to be the thing that changes the direction. But the number that we're using for A is what's going to change the width of the graph. So I'm going to go ahead and look at the section right here. It says a vertical stretch and or compression is a change in width. That is going to change our graph to either something wider or something thinner or narrower compared to the parent function. So if you keep on reading, the difference between a stretch and a compression is whether it gets narrow or thinner or wider than the parent function. So notice that there are specific numbers that will make our graph thinner, and there are specific numbers that will make it wider. So if you look right here, if we're going to make our graph narrower or thinner, our A value is a number that's greater than 1. A has to be greater than 1, and that can be anything from 1.5 to 3, 4, 5. All those numbers are greater than 1. Now, if we're going to do a vertical compression, which is going to make our graph wider, our A value is not just going to be less than 1, but it has to be between 0 and 1. So we need a number that is between 0 and 1, like a fraction or a decimal between 0 and 1. So remember that the negative, when you're using a negative number, the negative actually reflects it across the x-axis, changes the direction, but it doesn't do anything to the width. That's the actual number itself, and that's what we're going to look at right now. So let's look at our first examples. So like I said, if you already have these graphs, let's go ahead and talk about them. So our original parent function is this one right here in gray. Our A value is the understood one. It's a positive one, that's why it opens upward, and the width is going to be 1. And if you look at our g of x, notice that it went from having an understood 1 to a positive 2. So if you look at the graph and you compare it to the parent function, you can see that the entire g of x function is inside the parent function because it is thinner than the parent function. So because our A value is greater than 1, it does slim the graph down. So we call this a vertical stretch when we have a thinner graph than the parent function. Okay? And that is solely because the A is greater than 1. All right, let's look at the next example. So notice that this is our same parent function. We're using the same points and the same graph for our parent function. We said that A is positive 1 because it's that understood 1 right here. But notice what we're comparing it to. We're comparing it to an A value of 1/3. Now 1/3 is not greater than 1, it's less than 1, but it's not negative. So as long as it fits between the numbers between 0 and 1, notice what it does to the graph. our entire g of x is on the outside of the parent function, and we can see that it is wider than the parent function. So this one is wider, and this is what we call a vertical compression. Okay? And if you take a moment to look at our third example here, same parent function, same points, same width, and it's still a positive 1, but notice that I changed my a value to a fraction, which is 0.5. Once again, 0.5 is between 0 and 1, so that is once again a vertical compression because our graph is wider. So notice that the entire graph is on the outside of our parent function. Now, one of the comparisons that I want to make real quickly is that notice which one of the two is actually wider. So if you're looking at 1/3, 1/3 is actually wider than 0.5. So the smaller your fraction gets, or the smaller the decimal you get, then the wider your graph is going to be. Okay, so there's different levels of wideness, and so depending on what your a value is, if it's a smaller number, then it's going to be wider than something that it is wide, but not as wide. Okay, so vertical stretches and compressions are a change in width, and we're strictly looking at the a value to determine if it gets thinner or if it gets wider compared to the parent function. Okay, and that is it. So just remember, vertical stretches and compressions are the width of our graph. So with that being said, that is all we need to talk about there. And so when you're looking at your practice problems and they're asking to determine whether something has a vertical stretch or a vertical compression, look at your graph, compare the width, or look at your equation and compare the a value to your parent function. All right, I hope that has helped. We're going to go ahead and pause and then jump into the next video so we can have a conversation about what a translation is. There's two kinds of translations, vertical and horizontal. I'll see you guys in the next video.